Okay, can you guys hear me? Okay. Hello, everyone. It's my honor to give a talk here at QCrypt. I am Wenyuan from the University of Toronto, and you can also call me Mike. Today, I'm going to talk about enabling a scalable, high-rate MDI QKD network. And note that this is actually different from the TF and PM QKD mentioned by Marco and Zhengpei here, and this is the original MDI QKD protocol setup. So let us begin. Here. So this is a joint work between the University of Toronto and the University of Science and Technology of China. So I'd like to sincerely thank the effort of all the people involved to make this project happen. Now, this work consists of two parts. The theory part has been devised at the University of Toronto, and the experimental part has been performed by the USTC group led by Fei Hu and Teng Yun. And our group will mostly providing the theory support and also the data analysis. And Fei Hu is actually here today, so if you have any questions about the experimental details. Oh, OK. Sorry. Yeah, safety measures. OK, definitely. Fei Hu is actually here today, so if you're interested in the experimental details, you can also ask him for more details. And now let us begin describing the outline. First, I'm going to introduce the background of our motivation of building a quantum network with untrusted relays and why MDI-QKD is suitable for the job. I'm going to also introduce previous MDI-QKD protocols and their limitations, namely the symmetry of the channels. That is, the two arms will need to have similar levels of loss. Then we're going to bring forward our theoretical results. We propose a new method that uses different intensities to compensate for channel asymmetry and lift that limitation. I'm going to introduce the physical intuitions of why our method would work effectively, and also the key challenge of implementing such a method, which is parameter optimization. I'm going to introduce how do we address that problem. Then I'm going to bring this into actual context and talk about the simulation results. And finally, I'm going to introduce an experimental demonstration of our method and show its effectiveness in a practical setting. So let us begin. As Marco has already kindly introduced this morning, MDI-QKD can eliminate detector side channels that are susceptible to attacks. It enables untrusted relay, this Charles or Charlie, that can be untrusted, and we don't have to make any assumptions for it. Now, MDI-QKD has seen a lot of experimental demonstrations. As Marco has listed again, I won't go into too much details here. But importantly, there has been a 3-user demonstration of a metropolitan MDI-QKD network at USTC. Now, one important limitation of MDI-QKD is that all those above-mentioned experiments are either performed over near-symmetric channels, which have similar levels of loss, or they have to deliberately add a tailored length of fiber to the shorter channel. That is actually because in the X spaces, MDI-QKD depends on Hall-Amendo interference, and thus depends on the symmetry of the arriving intensities of the WCP sources. If there is a symmetry of the channels, then after the attenuation, the arrival intensities will be mismatching, and that would degrade the H1 visibility, thus causing a larger QBER in the X spaces and a lower key rate. For instance, from this plot we excerpted from the, this reference below, we can see that the visibility is the best when the photon number ratio is matching at the receiving end of Charlie. And then as it deviates from this value, the visibility will drop and causing the key rate to drop as well because of higher QBER. Now, we believe that the future of MDI-QKD is to implement an MDI-QKD network. It has the great advantage of enabling the use of untrusted relays, while many implementations of QKD networks so far are based upon trusted relays. An important requirement for one of such networks is that it should be able to dynamically add or delete nodes. For instance, for an existing network like this, if you add a new user like this, then it has to be able to adapt to those new pairs of connections between the new user and the old users, and establish connections according to those pairs of channels. But one problem here is that in reality, in a QKD network, we might often encounter pairs of asymmetric channels that might be caused by different geographical locations or by moving platforms over free space if we want to do MDI-QKD in free space in the future, for instance, between ships and ships, hot balloons, or even ground satellite links. So previously, in experiments, people have made a makeshift solution. That is, they actually add additional loss to the shorter channel in exchange for better symmetry. For instance, here, if Bob has an asymmetric channel, he might move back in his lab a little bit and add an additional tailored fiber spool in his lab. But we asked the question, is this really optimal? Well, the answer is no, because intuitively, this length of fiber is controlled by Bob safely in his lab. But by assuming a symmetric model and calculating the key rate, we're effectively yielding the control of this length of the fiber to E. And that is not the most efficient way to make use of the information. So here, we will propose a new method to show that dramatically higher key rate can be achieved by Alice and Bob compensating the loss with their intensities alone. So now let us introduce our theoretical results. And before this, I'm going to first introduce a previous protocol, the 4-intensity protocol, which has been introduced by Marco kindly too. So the key point here is that decoy state is only needed in the x basis and not in the z basis. So we perform decoy state analysis in the x basis and estimate the single photon contributions. The entire z basis, the signal states, are used for key generation. Thus, it makes it more robust against finite size effects. But this 4-intensity protocol paper limits the discussions to symmetric channels as well. So the channels are symmetric, and Alice and Bob will use the same intensities. So here, we apply our method and allow Alice and Bob to freely choose a different set of intensities. That is SA mu A nu A and SB mu B nu B, as well as the vacuum states. Now, before we talk about how do we choose those optimal parameters, let us first introduce the physical intuition of why such a method would work against asymmetry. So when we look at the key rate again, it consists of two parts, the error correction part, which comes from the signal states, and also the privacy amplification part from the decoy state analysis in the x basis. Now, this x basis is dependent upon Hall-Mendo interference, so it requires highly symmetric receiving intensities at Charlie. That is, this mu A eta A, where eta is the transmittance, has to be similar to mu B eta B in order for a high visibility to be maintained and the QBR to be low. But we make the important observation that the z basis of MDIQKD is not related to edge element interference. In fact, it's caused by imperfections only, such as misalignment. If misalignment is 0, there will be no QBER. So this is an entirely different behavior than the x basis. It's much less sensitive to the arriving intensities. So generally, SA eta A is not equal to SB eta B. And the signal states will need a trade-off between two parts, this probability of sending single photons, and also this error correction that comes from this QBER. So the actual optimum values are usually found by numerical optimization. So now, the reason for our protocol to work is two kinds of asymmetries. The first kind is an asymmetry between Alice and Bob. They choose different intensities to compensate for the channel loss and get a good visibility in the x basis. But moreover, there's an asymmetry between the x and the z basis as well. That is because, as we said, the x and the z basis have very different reasons for the QBR and behave very differently in the presence of asymmetry. So by decoupling the x and the z basis for optimization, we can choose different strategies for the decoy states in the x basis and the signal states in the z basis for an optimal choice of intensities and a best key rate. So now, having defined the intuition, let us introduce how do we choose the best parameters. There is, in fact, a big challenge here for the parameter optimization because of simply how many parameters are involved here. There are as many as 12 optimizable parameters. In fact, if you use a powerful workstation PC, it takes approximately 4 months to use a very coarse 10-point resolution search, and it would take 3 times 10 to the power of 11 years to search for a moderate 100-point resolution. And by the way, that's longer than the age of the universe. So definitely, this is not a practical solution. And we have to use a local search algorithm called coordinate descent, which was used by our group in a previous work in 2014. Now, the coordinate descent works like this. So instead of searching the entire picture, let's have an example of just SA and SB, two variables. So instead of searching the whole picture, you iterate along one coordinate at a time and fix the SB here. Only search SA. Once you find the best point, you can search along SB and fix SA instead. Now, you search SA again and SB again. So by iterating like this until you reach the local maxima point, it is shown that this method is in fact equivalent to using the gradient descent method, which some of you here might be familiar with if you're doing optimization or machine learning. So such local search algorithms can have a search time that's linearly related to the number of variables rather than exponentially, so it's a lot more efficient. But the problem is, the bad news here, is that coordinate descent doesn't work for non-smooth functions. And unfortunately for us, asymmetric MDI-QKD key rate is not a smooth function. And here we will show two theorems here for asymmetric MDI-QKD. First, there's a non-smoothness of the key rate function, and there's a ridge that can be observed here at mu A over mu B equals nu A over nu B. And second is that there's a proportionality of the optimal choice of intensities. That is actually to say, the key rate optimal points always happen on the ridge. So combining those 2 points, we can actually devise a very clever workaround. That is, instead of using the Cartesian coordinates, we can instead use the polar coordinates. And we know those polar angles will be the same since they're proportional to begin with. Then we can jointly search those 2 polar angles for mu and nu. Now this key rate is a smooth function versus this theta mu nu, for which we can perform efficient parameter optimization. Graphically, this means we're always walking on that ridge, and we're never deviating and wandering off it. So now, on a quad-core PC, it only takes 0.1 second to efficiently search any given point, any given set of parameters. That is over 100 million times faster than brute force search, and in fact, it can enable a real-time deployment of such an optimization method on the field. Because it is so fast, it will tell you the optimal parameters right away. Now, let us introduce the simulation results. So first, we plot out the 4-intensity protocol, which uses the symmetric intensities over LA and LB. As we can see, the contours of the key rate is limited to the symmetric regions, which is close to the diagonal line. And as it deviates from the symmetric point, the key rate will degrade very quickly. But now, with our method, we can see that we have a much wider applicable region for MDI QKD with good key rate. In fact, even at highly asymmetric cases of 100 kilometer and 0 kilometer, you can still get a good key rate. So we have a much higher freedom in choosing the channels of MDI QKD. Now, when we look at the key rate too, compared with the original results, we can see that our results have much higher rate and also much longer distance. For instance, for the solid line here, which has a 50 kilometer difference between Alice and Bob, you can see there is an 80 times higher key rate than previous protocols. And also, even with a moderate level of asymmetry of 30 kilometers, you can still get 300% the key rate. So the higher the asymmetry is, the more advantage such a method would gain. So now, let us also have an example of a realistic QKD network. So we use the channel models from the Vienna QKD network and excerpt 5 points from it. We assume that this middle point, A2 here, is the untrusted relay. Now, the question is, this longer channel of 85 kilometer cannot establish connection with the other users because of this high asymmetry. If you choose to add fibers here, then you will get a non-zero but very low key rate. And in addition, you have to physically modify the channel of every user to accommodate for the longest one. However, with our new method, you can have 3 orders of magnitude higher key rate while you don't have to modify the channel at all. So this allows for a very important scalability of our protocol. That is, adding new nodes to this network does not affect the existing nodes. So that goes back to our initial picture. So if you add a new connection like this, the protocol would be able to optimize those new pairs of connections independently and establish the new connections without affecting the existing connections, allowing for this scalability. Now, let us introduce an experimental result performed at USTC. So this experiment is based upon a time bin phase encoding system. It ensures an H1 interference visibility of up to 46% and an amplitude modulator extinction ratio of more than 23 dB. Here are also the information of the system clock rate, the detector efficiency, and also the detector doubt count rate. Now, importantly, in addition to maintaining a balanced receiving intensity by modulating the intensities according to the channel asymmetry, more aspects has to be considered to ensure the indistinguishability of the arriving signals. That include the timing indistinguishability, the spectrum, the polarization, and also a stable phase reference frame. So the system actually makes use of an automatic feedback system that can maintain a long-term stability of the system over tens of hours. For this experiment, it is performed over 2 scenarios. In the first case, we fixed the shorter channel to 10 kilometers and then searched the long channel between 40 and 90 kilometers. We test the different cases of using added fiber or not using added fiber and using our new method. As we can see from the results here, the experimental results, those dots, follow the theory predictions, which are the curves here, very well. Our new method here is the red line, and this is adding fiber, and this blue line is the case where you don't add fiber and you use symmetric intensities. As we can see, at this 10 kilometer, 60 kilometer point, which is this point versus this point, our rate is over 3,000 times higher key rate than that of using the 4-intensity protocol. Also, with our new method, we can gain a 40 kilometer longer key rate than previous protocols. We also study a very interesting scenario in the second case. That is, one of the channel can in fact be 0 kilometer, and the other channel is very long, from 40 to 100 kilometer. This is actually what we call a single arm setup, because in effect, Charlie and Alice can be placed inside the same lab. So viewing from the outside, there is only one external channel, making this a 2-party protocol, but it's still guaranteeing that security against detector attacks of MDI QKD at Charlie. So this could be also important if this is a free space channel and you want to perform MDI QKD across it. Now, when we study this key rate again, we see that it also follows the predictions very well, and the new method maintains a good key rate even when the LBC reaches 100 kilometer and the LAC is 0, which is a highly asymmetric case that previously is unimaginable with MDI QKD. So now, as in conclusion, we propose a software solution that maintains good performance for arbitrary levels of asymmetry between channels. There's no need to add any loss and no need to modify physically any part of the channel. The optimal key rate is achieved by optimizing the intensities alone. This could be very important because it can be integrated readily into existing infrastructure. Because this is a software solution, it doesn't need modifying the physical part of the system. We also have extremely fast optimization algorithm in less than 0.1 second, which means it's readily deployable to the field. And finally, there's a reconfigurability that allows dynamically adding and deleting nodes without affecting existing nodes. So overall, we have proposed a solution to enable a high-rate, scalable MDI-QKD network with arbitrarily placed nodes rather than symmetrically placed nodes only. So here are the acknowledgement and the funding information, and here are the references to the theory and the experimental paper, which are both posted in our archive. So if you're interested, do please kindly check it out. If you have any information, please feel free to ask me or Feihu after the break, and also contact me via the email address. So thank you very much for this opportunity.
So now talk is open to discussion.
Thank you for this very energetic talk.
Thank you.
I was curious about the optimal photon flux that you find.
Yes.
If they are very different from from those that one would intuitively expect. For example, I don't know. After in the case with 0 kilometers and 100 kilometers, you have an initial photon flux, and then after 100 kilometers, you have an arrival photon flux.
Yes.
The one that you put on the 0 kilometer channel is similar to this intuitive one, or is very different?
So here actually, we actually have a backup slide for this. When we look at this, so for instance, here I actually plot the case for the 10 and 60 kilometer case. But it's similar, so there's a 50 kilometer difference. As you can see, the intensities for the SA, which is actually the shorter channel, is actually stronger. But the important thing here is that the SA versus SB is not really following that difference in the eta A, eta B that much. Because as we said, it has a trade-off between the signal intensity, like between the photon probability and the error correction. And it's not that sensitive to the arriving intensities. But when you look at the mu's, here is 0.5, and that is 0.05. So that actually compensates for that 50 kilometer, which is 10 dB of difference in the channel. So the mu A over mu B will follow the, so actually this part will show it better. So this is mu A over mu B, this is SA over SB, and we fix that mismatch and then scan it at a different point. As you can see, this mu A over mu B follows that, this 10 ratio of the transmittances of the channel very well. So maintaining a good photon flux for good H1 visibility in the X spaces. But the signal states are not involved in this, so they have more freedom to optimize over it. So they change rather freely.
Thank you.
Yes.
Other question or comment? No. Over there.
I have one question about your network approach. I mean, you have plotted some network, but it appears to me, maybe I'm not wrong, so this network can be prolonged in theory indefinitely, but for every single user, there is a maximal distance that can reach in this network. So it's not a network in the sense that anybody can communicate to anybody, but anybody actually up to his maximal radius. Do you?
Yes, so in our setting, I'm sorry, I probably didn't hear the question that clearly, but if I'm assuming your question is asking, is there a maximal distance for the users? Then yes, because one relay actually connects a radius of users around it. So in fact, if you want to connect to users, you have to have at least one relay between them, because if you want to exchange the information between relays, that makes it untrusted again. So unless you have quantum repeaters or entanglement sources. So here, by talking about this protocol, we're talking about probably more of a medium distance. Let's say a metropolitan setup where you have many users that are randomly distributed near or far. Now, if you have the previous protocol, you have to have a symmetric link to every pair of them. But now we have a much better use case that as long as you have a relay between them, it doesn't matter where the relay is placed. It will always establish a good connection regardless of the asymmetry between the pairs of channels. But yes, there is still that maximum distance limit that, because ultimately this, we're compensating the intensities, but it's still MDI-QKD. It depends on a two-photon interference passing through the channel. So unlike TF-QKD or PM-QKD, which actually depends on the singles instead of the coincidences of the two photons. So the scaling will still be actually eta square. So it will have a better scaling coefficient, but the scaling will still be eta square.
Okay, thank you.
Yes. Oh, and one more point. I think we, in the appendix of our paper, we actually proved that the scaling is actually related to the longer of the two channels. So if the asymmetry is very large, it doesn't really depend on the shorter channel anymore. It scales with the longer of the two channels. I think we have we'll have a plot here somewhere. Yeah, like this. So it actually, the scaling, so unlike those single photons, which doesn't really depend on the asymmetry, we can see here that the contour of this key rate is perpendicular to the axis, which means if the longer channel, let's say, is this 250 kilometer, then the shorter channel doesn't really matter that much. It scales with that longer channel. Any other questions?
No more questions? Okay, let's thank the speaker again. Oh, sorry. Here.
Have you tried to use your optimization method to optimize the encoding of the states? I mean, choosing the number of tie beams or intensities in the states?
Sorry, I didn't hear the question that clearly.
Because you proposed an optimization method for several parameters, but have you tried to use it to optimize the encoding of the prepared states, like choosing a different number of time beams or different intensities in the prepared states?
Yes, so the optimization here is not considered using different number of decoy states, but we believe that a similar approach should be able to apply it for that, because in fact, this plot in the backup slide is using infinite number of decoys. So this is the asymptotic scaling of what it looks like. This is what previous protocols, that SA and SB are equal, and here is our protocol. So here, that scaling is actually resulting from the asymptotic limit. So no matter if I use 3 decoys and 4 decoys and 5 decoys, let's say, in that X spaces, it would have a trade-off between a good estimation of the single photons versus the finite size effects. But all in all, we believe that our analysis here will be applicable to all those cases, let's say, different number of decoys are used, too.
Okay,
Thank you for the question.
Okay, let's thank the speaker again.
Okay. Thank you very much.